We have been talking about phase. Well, first, actually, we started talking about this whole chapter of solids and liquids. We talked about solids and liquids for a good deal of time, a few days maybe, not very long. All right, but then we spent a lot more time on phase changes, and we looked at phase changes a lot of different ways. We looked at it in terms of an equation, in terms of Le Chatelier's principle, which is going to be favored if I change things on them. All right, we've even graphed them yesterday. We graphed them in a graph like this, and we graphed them in a different kind of phase diagram. Well, now we're going to do some math with them. We're going to actually calculate the amount of energy it takes to change phases. We're going to do some numbers with it. Okay, I told you there wasn't a whole lot of math in this chapter, and this is it. This is the good news, because if it was all questions, you'd do even worse in the test. The math at least gives you a chance for partial credit. But the math isn't that easy. It starts out pretty easy today. Today I'm going to show you how to do two different kinds, but then we're going to put them together tomorrow, and it's going to get kind of complicated. All right, now here's my basic phase change graph. We saw this yesterday. This is what the lab's on tomorrow, and it's what the calculations are on today. Those are your three phases: solids, liquid, and vapor, and that's where they exist. What do we call these parts here? What's happening here and here? Melting and boiling. Okay. So what I'm about to show you is how to calculate the amount of energy it takes to melt or boil something, or and vice versa, how much energy would be given off if something were to condense or freeze. Remember, energy is given off. Remember, I held that test tube. I passed it around. It got hot when it froze. Okay, so the amount of energy, I'm going to show you how to make that calculation, and then the second half of the class, I'm going to show you how to make, well, actually, I'm going to do it all at once for your class because you don't have a double. I'm going to show you how to do the calculations for just a simple temperature change, like heating up a solid or a liquid or a vapor. And all of that's going to be calculated in, what's my unit of energy? We don't use it very often in chemistry, at least not in Chem 1. You do it a lot in Chem 2. What's our unit of energy? From physics, you know? Joules, absolutely. We're going to use joules. So we're going to learn how to do some phase change calculations today.
Mr. Allen, I think I left my book in here, so when we're done, can I check the closet?
All right, phase change calculations. We got to use something called the heat of fusion or the heat of vaporization. Fusion meaning what's going on at the melting freezing point. Okay, vaporization, I think everybody knows what that probably means. What's happening at the boiling point. Basically, you have to be told some information. I'm going to give you 5 numbers today that you do not need to memorize. I've only made you memorize a few things. No dates, very few scientists, and very few numbers. About the only one I could think of, the only couple I could think of is 6.022 times 10 to the 23rd, Avogadro's number. And in one chapter, R for 0.0821 liter atmosphere per mole Kelvin. But you use it so much you didn't even have to memorize it. The numbers I'm about to show you here, you do not need to memorize. It's going to be 5 numbers by the time I'm done here. All right? We'll start off with the heat of fusion and heat of vaporization. What is it, and what are the numbers for water? Because water is the big guy we use most of the time. The heat of fusion is the energy required to change the phase of 1 mole of substance. If I'm talking about changing the phase from a solid to a liquid, I'm talking about the heat of fusion. If I'm talking about changing the phase from a liquid to a vapor, I'm talking about the heat of vaporization. And I just have to give these numbers to you. Actually, it's not true. In lab on Tuesday of next week, you're going to figure it out for me and see how close you get. But in the problems, I have to give you these numbers, and here they are. Heat of fusion of water, HF, that's what HF stands for, heat of fusion. Heat of vaporization, HV, of water, are right there. 334 for the heat of fusion, 2260 for the heat of vaporization. Before I even begin the first problem, I have 2 problems of these type to do. Let's just look at those 2 numbers and see how they differ by so much. Heat of vaporization is very high for water. It takes a lot of energy to boil the same amount of water. By the way, this is joules per gram, right? So for 1 gram of water to be boiled, it's going to take 2,260 joules to boil that water at 100 degrees Celsius. Where it will only take 334. So that tells you something. That's the reason why you have those big stacks in front of the nuclear power plant up the road. What are they doing up there? What's coming out of those stacks? Okay, notice you almost want to call them smokestacks, but it's not smoke, it's steam. Because water is it's really hard to boil water. And so it's a great coolant. The amount of energy it takes to boil a gram of water is very high. So you basically use it as a coolant in your car. It doesn't boil very easily. We want it to cool things down, to be used as a coolant. That's what it's used at the power plant and a lot of places. All right, having said that, we don't care. We care more about getting the problems right. So let's get to the problems. All right, here's the kind of questions I might ask you about. Okay, say I have a sauna. Maybe you've been into a sauna sometime in your life. You pour water on hot rocks or whatever, and the water is converted to steam. It basically, you can see it being converted to steam. If I convert 122 grams of water into steam, how much energy did it take? How many kilojoules of energy were required? Now, I'm not even, these problems, these first ones I'm showing you today, first two examples I'm going to show you the first part of the class. They're so easy. I don't even have a formula to write down for them. It's more like a conversion than a formula. And without me telling it to you, as we go on throughout the year, I've given you very, I think, almost babying you in the way I was teaching you how to do a lot of the math stuff. Okay? Let's see if we can figure this out without me babying you. I got the wrong answer in the last class for the first one. Maybe I'll get the wrong answer here. What do you think I'm going to do to get the answer here with these numbers? Raise your hand if you think you know what's going to happen. What do you think? Bob?
Do the amount of water, the 122 grams.
122 grams. What am I going to do with that number?
Multiply it by 2,200.
Okay, good. That's the correct answer. And let me explain. For those of you who weren't thinking that, I'll also explain the mistakes I was looking for. First of all, he picked the right guy. It never said to use the heat of vaporization. But look at the question. The question says water is converted to steam. Which one do you think I'm going to use? This guy. Okay. Second, he did the right thing with it. He multiplied 122 by that guy. Last class, they divided them. Okay. How do you know you'd have to multiply just looking at the units? What's going to happen if I multiply grams by joules over grams? What's going to happen to the grams? Yeah, I'll have just joules left and grams will cancel. So that's all you do in these. That's how easy they are. You simply take, by the way, right, you have to do something else after that. So make sure you have enough room sideways here. You simply take 122 grams and you multiply it by the heat of fusion, in this case, 2260 joules per gram. Grams will cancel and give you what? Do that on your calculator. What do you get? Should have three significant figures for your answer, and what did you get? What did you get, Zach?
276 pounds.
Anybody else get that?
Okay.
That look good there, everybody? All right. Now that's in joules. What did the question want? Yeah, I could do this. I could ask you for it in kilojoules. What would you do now? You convert it. Joules on the bottom, kilojoules on the top. Same way we learned in chapter 1 or 2 whenever we did that. 1 kilojoule contains 1,000 joules. You don't have to even show this. If you could do it in your head, that's fine. 1,000 into that, you're going to get 276 kilojoules, which explains why I would want to have this guy in kilojoules, because it's such a big number. I wouldn't want to have it in just joules. Okay? By the way, 122 grams of water is not a lot of water. It's about a cup. It's 120 milliliters of water, right? 122 milliliters of water. And that's how much energy it takes to boil that, okay? To convert it to steam. Assuming it was already at boiling point. It was already at 100 degrees. All right, now, that's pretty easy. How can I make this a little bit harder? What can I add one more little thing to this? That's my second example is going to have. Watch. You see if you can tell me what I did different here. What did I do different? I don't. No. Yeah, it's moles instead of grams. Yeah. So I didn't do it backwards. I could ask you for it backwards, but I didn't. I asked you in this case. I gave you moles, and I instead of giving you grams. So I'll have an extra step there too. Let's take a look. What you do here.
Who's videoing?
Mm-hmm. And we need to use this one because your class was broken up more than you will be. This is the one I want to put up.
This is for Trent.
This one goes out to Trent. Hope you're getting better, Trent. We're praying for you.
I can't wait for next year's kids to watch this.
Mm-hmm. They're going to know you guys. They're going to know Emily. That's for sure. All right. Y'all got that copy? All right, look at. Problem is, I have joules per gram, but I'm given moles. So what do you think I'm going to have to do first?
Moles are moles.
Yeah, I'll have to convert my 2.00 moles to grams. Moles go on the bottom, grams go on the top. 1 mole contains sodium is 22.990. And I'll get, by the way, I don't even have to hit equals here. Let's not hit equals this time. Let's just keep going. All right. What can I do now? I don't need an arrow there or a blank there. What can I do now? That will get me grams, right? What do I need now? Times it by the heat of fusion, 113 joules per gram. Grams will cancel, and that will leave me with my answer. So just do them both at once this time. Yeah, you notice this time it was a different substance. Different substances have different heats of fusion. Sodium does not have the same amount of heat of fusion as water does. Yeah.
Do you do significant figures with the, or is that like the standard?
You always use significant. Oh, you mean for this guy? No, that would be 3 significant figures. That would limit you. Yeah, that would limit you. And you have 3 here anyway, and you have 3 here anyway, so it wouldn't make a difference in this case. What do you guys get for your answer? Somebody? And what'd you get, Ben?
5,200.
5,200? It should be one more significant figure or no?
No. It rounds up.
Oh, it rounds to that? Okay, so 5,200 joules. Okay. Would be the bar would be over that then, right?
Sure.
Just because that would be 1, 2, 3 significant figures.
Oh, okay.
Okay. Not a big deal. All right, good enough. Now, at this point, I split the air class, which was a double period, up into 3 parts. I stopped here, let them work on a few problems that are like this. Then I taught them again the next type, let them work on a few problems like that. And then I did the combined ones and let them work on a few problems like that. You guys only have 1 period now and then 1 period tomorrow. So I'm going to keep going and show you the next type of problem I can have. And that type of problem, if you take a look here, is at these points. Take a look. What did we just do? We just learned how to do stuff here and here, between the melting point and the boiling point. We know what to do there. Okay? If I tell you how much energy or how many grams I have, and you know how much energy it's going to take to boil it, you know how much energy it would take to melt it. What I'm about to show you now is how much energy it takes just to change the temperature. Just to go from here maybe to there. Or just to go from here to there. In the same phase. In the same exact phase. All right? Now, I want to ask you a couple of questions about this. All right? Think about this. If I'm going to heat 2 things up, I want to heat 2 things up. Why might it be harder to heat? Because, by the way, this equation is harder than the last one. The last one was a simple conversion, really. This one's going to have several factors involved in it. Last one, all it really mattered was how much you had. All right? Once you knew the heat of fusion and you knew how much you had of it, you were good. This one, it's got 4 variables. Well, not including the actual answer you're solving for, the heat. It's got 3. What are some factors? If I have 2 things I want to heat them both up, what's going to make it harder to heat one up than the other? Anybody? It's very simple. Okay. Why would it take more energy to heat one thing up than something else? What could be different about them?
The
The
temperature that they are.
The temperature. Very good. Let's start with that one. That's an easy one. And that's absolutely one of the factors, temperature. If I want to heat one 10 degrees higher, I'm going to heat the other one 30 degrees higher. It's going to take more energy to heat the one to 30 degrees higher. Great. What else? Let's say I'm going to heat them both to exactly the same temperature. What else? What's that? Okay, so what the stuff is made out of. Absolutely. It's going to be a heck of a lot easier to heat up metal than it is to heat up water, than it is to heat up air. All right? That's why we use air as an insulator. That's why we use metals as a conductor. Okay. So what it is we're heating up and how hot we're heating it to, how high temperature we're heating it to. What else? How much of it there is. I have the same 2 beakers. I have a beaker of water Another beaker of water here. Going to heat them both to 80 degrees. They're both water, but one's bigger than the other one. I got more water in the other one. It's going to take more energy to heat the bigger one. That's why the equation for the temperature change calculations looks like that. Whoops. That's why it looks like that. Delta H is going to equal MC delta T. Because the three factors you just told me about are all involved there. You said about, last one you just said, Maddie just said, was how much you have of it, the mass of it. That's what the M stands for, right? What do you think the T stands for? Temperature. And what do you think delta in front of that T means? Yeah, so how high you're going to heat them. All right? And the C, that's the guy you don't know yet. I'll save him for last and tell you what he is, but that has to do with what substance he is. All right, so let's do this thing. What do each of those four things stand for? What do you think delta H probably stands for? The change in heat. Absolutely, the heat change. How much energy it takes, how much heat energy it takes to do this. That was basically what I was calculating just a few minutes ago. But at the heat of fusion and heat of vaporization, I was calculating the delta H, all right, by simply multiplying the heat of fusion times how much you have. That's all you had to do. But now we got to take into account how much we have. Obviously, M means mass. We got to take into account the temperature change, delta T, how high you're heating it to. But we also have to take into account this other thing, C. C is an indicator of how easy or how hard it is to heat up this stuff. If it's a metal, it's going to be real easy to heat up. If it's water, it's going to be a lot harder. It's called the specific heat. And it measures how hard or how easy it is to heat up something. Now, the thing is, everybody's got his own specific heat. Everybody has their own specific heat. Different things are easier. Other ones are harder. And even different phases of the same thing can be easier or harder, as you'll see with water. The guy we use most of the time is water. He'll be in most of my examples. So let me give you, I already gave you two numbers I told you didn't have to memorize. Here are three more. The specific heat of water is 4.184 joules per gram degree Celsius. I'll talk about those units and why they are what they are in a minute. For liquid water. But it's different for solid water, and it's different for gaseous water, steam. Write all those down, and the answer is no. You do not have to memorize them. They'll be written on the top of the test. They'll be written on the board. They'll be written somewhere every day. They're just constants you can look up.
But will we probably remember them?
No, these are not ones, like for example, most of you have already memorized 2 or 3 atomic masses because you use them so much, like oxygen and carbon, because we use them all the time. Maybe even sodium or chlorine, because we use them all the time. This is not, we're going to use this in this chapter. We're really not going to use it again until, I don't know if I've mentioned this, but this whole thing, this equation, and this whole topic is an entire chapter in Chem 2. It's called thermodynamics. And we'll spend a lot more time. I'm really giving you a simplified version of specific heat. And remember, there's even a special name for the delta H we're going to get. And the values being positive and negative are going to mean something. I mentioned that. It's called thermodynamics. Delta H is actually called enthalpy. But none of that stuff do you really have to worry about right now. You just have to be able to use this equation for this chapter to explain how hard or how easy it is to heat up substances and be doing the calculations for it. Okay. That's basically the information you have. Let's do an example. Okay? Copy that one down. How much heat is required to raise the temperature of 43.8 grams of water from 23 degrees Celsius to 97 degrees Celsius? Now, it may seem like, well, let's just plug them in like I did a minute ago. I don't really need to write the stuff down to the side. Look at last example we did, there really wasn't even an equation. I could have made an equation up for it, but the fact is it was almost like a conversion. This guy is an equation, and like all equations I've given you, I really want you to write the stuff down to the side, give me the equation, rearrange it, do all that stuff, so I can give you partial credit, and so you don't get the answer wrong as often. So I do want you to write this stuff down to the side. You know what equation you're using. Delta H equals MC and delta T. Oh, I almost forgot. I did forget to mention a second ago. You can write that down. But under delta T, it's important that you realize, when you look back to that guy, you have to have, delta T has to be TF minus TI. What do you think F and I pi stand for? Final minus the initial. All right. They say, well, why does it have to be that? Because it's going to be the same thing. Well, it's a convention about whether it's positive or negative for delta H tells me whether it's endo or exothermic also. All right. I'll talk about that at the end of this problem. All right. Let's get back to this guy here. So delta H, MC, delta T. Can we pick all that stuff out? Delta H is obviously what?
What we're trying to find?
Right. It's the unknown. The mass is clearly 43.8 grams. Now, here comes a reason why there's two reasons I want to write this guy down to the side. And it's going to become even more important for the combined calculations. Reason number one, which C am I using? It doesn't specifically say. Specific heat specifically say. It doesn't specifically say which one to use.
Liquid?
But why am I using the liquid one?
Because that's a normal liquid temperature.
All right, good. All right, I don't like kind of the way you said it, but because water is a liquid between 23 and 97 degrees. That's why. All right? And we are talking about water here now. So since we're talking about water, water's a liquid. If these temperatures had been 110 going to 140,
Solid.
it would have been 110 going to 140?
Oh.
Would have been what? Gas. And if it had been minus 20 going to minus 50, it would have been, I would have used the C for salt. Okay? So I have to use the one for liquid. That's 4.184 joules per gram degree Celsius. I told you I was going to talk about the units. I'm getting there. Okay? Finally, we got another reason to write this guy down is delta T has to be TF minus TI. Just to remind you of that. TF minus TI. If I don't do that, I'll get the wrong sign. Same answer, but wrong sign. Positive versus negative. My TF, it's going to 97.0 minus my TI, which is 23.0. So what do I get when you subtract those in your calculator? 74.0 Celsius. All right. So that's the reason I write this stuff down this side. I really need to do those things to pick out the correct specific heat, to make this, make sure I don't do the temperatures the wrong direction, and then I can very easily plug in my equation. Delta H equals MC delta T. I don't even have to rearrange it. It's set up to solve. So I'll just do M, which is 43.8 grams, times C, which is 4.184 joules gram degrees Celsius, times TF minus TI, which is 74 degrees Celsius. Notice the 74 is positive because of the way we subtracted it, TF minus TI. Now, it's time to talk about why. I wanted to point out to you why specific heat has the units it has. We've already seen that the units of constants are sometimes kind of weird. All right? And sometimes in the case of R, for PV equals nRT, they're really weird. R is liter atmospheres per mole Kelvin. I can't even visualize that. In the case of specific heat, actually it makes complete sense. And it makes the units work out. Specific heat has the units of joules per gram degree Celsius because here's the definition of specific heat. It's how many joules, how much energy it takes to heat up 1 gram of water, 1 Celsius degree. So it makes complete sense both in the definition and it makes complete sense when you plug it into the equation because guess what happens? Everything cancels out and leaves you with the units you'd expect to get, which are joules. What's my final answer for that guy? I don't know. Jared, what'd you get for your answer for this guy?
13,000. What is this? 3? Yeah. And then 600.
Anybody else get that? Good there, everybody? Okay, and that's in joules. And that is your answer. Okay? Hey, now, here's the problem. I want to hint it to you right now before I shut the camera off and let you work on the problems for the last 15 minutes or so. Okay? I'm going to hint at this right now. Watch. Everybody go with that one? Or do I have another one I wanted to do with this one? I think I might. Let me see. Oh, yeah, I do. Yeah, we better do this one first. I'll just save that other one for tomorrow. Let's do this one first because there's something else to watch out for in this one, too. It's not that big of a deal, but we better do it. Should be able to do it pretty quickly. Just be careful with your negatives in this one, and be careful with what C you pick this time, too. Delta H is obviously the unknown. M is obviously 28.0 grams. Specific heat, which one am I using?
You're gonna use the solid?
Exactly. 2.09, I think it is, right?
Yep.
And my temperature change, be careful of this one. It's TF minus TI like it always is. Oh, and I forgot, I'm glad I'm doing this one too because I forgot to mention something about the previous one. It's TF minus TI like it always is. Let's do the TF. The TF is what?
Negative 12.4.
No, it is not. It says it's cooling from minus 12.4 to negative. So you must read it correctly.
You wanted me to say that.
No, I didn't. I wanted to make sure that you guys don't get that right. Wrong. Now here's the crazy part too. Besides getting those backwards, I got to go minus a negative 12.4 degrees. Okay. So basically, yeah, you're basically adding 12.4 onto a negative 57, and what do you get? What'd you get?
Negative 44.6.
Negative 44.6 degrees Celsius. Sound good to everybody?
Yes,
Okay.
buddy.
All right.
Yes, buddy.
That's my dog's name. Okay, delta H equals MC delta T. So it equals 28.0 grams times 2.09 joules per gram degree Celsius times negative 44.6 degrees Celsius. What is delta H in this case? Mark, what'd you get?
Negative 2,600.
Anybody else get that? So good?
No, joules.
Right, good. Joules. And here, now look, don't close up yet. There's something I forgot to tell you last time. I want to make sure I tell it to you this time. We'll go back to there and change it. I told you a little while ago that the sign makes a difference. In Chem 2, you're going to learn about that a lot more. It's going to tell me whether it's positive negative is going to tell me whether it's endo or exothermic. But I want you, there is a convention about that. Positive means one and negative means the other, but you can now tell me. I got a negative answer for this. Read what happened in the question. This stuff went from negative 12 down to negative 57. Did it absorb energy to become negative 57, or did it have to give off energy to become negative 57? It had to give off. Yeah. So that makes this guy what?
Exothermic.
Exothermic. You should write exothermic down next to the answer to this one, and the previous one we just did. Okay, let's take a look. Maybe sometimes it's harder for people to see that one. This one may be easier. This guy, the previous one, went from 23 to 90. There's no negatives in there, it gets confused. 23 up to 97. To do that, wouldn't you have to put him on the stove and give him energy? Wouldn't you have to heat him up? Wouldn't that make him, and write that underneath your answer to that one, endothermic?
Yes.
Okay? All right. Tomorrow we will put these guys